Welcome to The Explainer. Today, we're diving into the science of probably the most important liquid on Earth, water. We're going to find out what makes it so incredibly special.
So have you ever been cooking or maybe just walking on the beach and wondered about this? Why does salt just disappear in water, but sand sits right at the bottom? Well, it's not magic. The answer is actually a hidden superpower baked right into every single water molecule.
Okay, so let's get right into it. To understand water, we first have to understand the one core property that makes it so unique, its polarity. So what is polarity? Well, if you look at a water molecule, the oxygen atom is a little greedy. It pulls the electrons closer, which gives it a slight negative charge. And that leaves the two hydrogen atoms with a slight positive charge. So you get this tiny little magnet. And this slight imbalance of charge, it's the secret to pretty much everything water can do. This little magnetic quality is why water gets this awesome nickname, the universal solvent. You could almost think of it as the social butterfly of the chemical world. It uses that magnetic pull to tear apart other charged compounds like nothing else. I mean, this is how nutrients get transported in our blood, in plants. It is absolutely essential for life as we know it. And here's a really simple trick to remember how it all works. Polar water loves polar things. It perfectly explains why stuff like oil and grease, which are nonpolar, just won't mix with water. They don't have that magnetic attraction, so they just ignore each other. All right, let's see the superpower in action. What is actually happening at the molecular level when we drop a little salt into water? You might think you're just stirring, but what's really going on is a full-blown molecular tug of war. The water molecules just swarm the salt crystal. Those negative oxygen ends, they grab onto the positive sodium ions. And the positive hydrogen ends, they latch onto the negative chloride ions. The whole crystal just gets pulled apart. It's a battle that water, with its sheer numbers, almost always wins. And this is where it gets really cool, because water can form three totally different kinds of mixtures. First, you've got a solution, like salt water. It's completely uniform, homogeneous, and the salt will never settle out. Then you have a suspension, like sand and water. It's uneven, and if you let it sit, the sand will definitely sink. But then you get the really tricky one, a colloid, like milk. It looks uniform, but the particles inside are just big enough to scatter light. That's a phenomenon called the Tyndall effect. Okay, let's switch gears a bit. What if I told you that sometimes water isn't a liquid at all, but it's hiding in plain sight, locked away inside solid crystals? This is what we call water of crystallization. And you really should think of these water molecules as a key structural ingredient. They are totally essential for giving a crystal its specific shape and sometimes even its color. A perfect example is copper sulfate. Its beautiful blue crystals have exactly 5 water molecules locked in for every 1 unit of the salt. So what happens when you take that water away, maybe by heating it? Well, the change is, wow, it's dramatic. That vibrant blue hydrated crystal just crumbles into a plain white powder. That powder is called anhydrous, which literally just means without water. You're seeing right there just how important those water molecules were to its structure. So we know water is a great solvent, but it doesn't just dissolve stuff. It can also get into some serious chemical reactions. What happens when water meets metal? Well, as we're about to see, the results can vary a lot.
Here's the thing. Not all reactions are created equal. It's a whole spectrum. On one end, you've got super reactive metals like sodium or potassium that react, well, explosively, even with cold water. In the middle, you have metals like magnesium that need the water to be hot to get a reaction going. And then way down on the other end, you've got metals like iron, which will only react with the high energy of steam. Now, trying to remember that order can be a bit much, right? So here's a fantastic little mnemonic to help you out. Cool kids make hot steam. Cool kids is for calcium and potassium reacting with cold water. Make hot reminds you that magnesium needs hot water. And steam, of course, points to the metals that need steam. Easy.
All right, for our last section, let's bring all this chemistry right back home, literally, to the water that's coming out of your tap. It's time to talk about hard water. You've probably noticed this, right? You go to a different city, and suddenly soap lathers up like crazy. Or maybe at home it barely works at all. That difference, it all comes down to dissolved minerals. Hard water is just water that's full of calcium and magnesium ions that have picked up on its journey through rocks. And to get a little more specific, there are actually two types of hardness. First, there's temporary hardness. This is caused by bicarbonates, and the cool thing is you can actually get rid of it just by boiling the water. But then you have permanent hardness. This comes from tougher salts like chlorides and sulfates, and you're going to need a chemical treatment, like adding washing soda to soften that water up.
And hey, of course, we've got a little cheat code for this too to help you keep it all straight. B-temp, C-sperm. Bicarbonates cause temporary hardness, and chlorides and sulfates cause permanent hardness.
But wait, before you go thinking hard water's the enemy, it's not all bad news. There are actually pros and cons here. Those same minerals, calcium and magnesium, are great for your bones and teeth. A lot of people even think it tastes better. The downside, of course, is that it weighs soap and leaves behind that crusty scale in your kettle and pipes. So, the next time you see that scale buildup, you can remember the incredible journey of chemistry that put it there, all starting from a single, slightly magnetic, polar water molecule on its way to your kitchen sink. It really makes you think, doesn't it? Is hard water a nuisance in your kettle, or is it a nutrient for your bones?